Backpropagation, on the other hand, computes the derivative with respect to all the input parameters in one pass-through. So the computation cost is independent with respect to how many design variables you have. Okay, so instead of having to repeat a calculation multiple times, you just do one calculation. How does backpropagation achieve that? So remember, in forward propagation, if I have W3 being the output of the product, my W3, my Wi dot is defined as the derivative of Wi, the ith intermediate variable, with respect to the quantity I want to differentiate, for example, x2 in this particular case. All right, so basically that's really the perturbation or the derivative of every intermediate variable with respect to the input. In backpropagation, we have Wi bar as opposed to dot. That's defined as the derivative of the final output with respect to that particular intermediate variable. Think of the difference here. In forward propagation, Wi is defined as the derivative of the intermediate variable. In the backpropagation, what's called the adjoint of an intermediate variable is equal to the derivative with respect to that intermediate variable, not of that intermediate variable. All right. So this actually naturally leads to the procedure going backwards, because what is the first quantity you know that has its adjoint? Well, in the beginning, we know we actually have no idea what is the derivative of f with respect to the inputs, right? That's the quantity we want to compute. We only know the derivative of the output with respect to the last, with respect to the result of the last computation, which in this case is the plus, because the last computation actually produces the output. So the derivative of the output with respect to the result of the last computation is actually 1, because it's the derivative with respect to itself. Okay, now the procedure goes backward through the chain of calculations. We know now the derivative with respect to the outcome of the last operation, the plus. The task now is to figure out now what is the derivative of the same output with respect to the inputs of this plus. That again is applying the chain rule, right? So df the inputs is equal to df the output times the output the input, chain rule. So, but this chain rule propagates the derivatives backward through the chain of calculations. So in this case, the derivative, the partial derivative of the plus is equal to 1. So the derivative with respect to W3 is equal to the derivative with respect to the W5, the output, times 1. Also, derivative with respect to W4 is also the derivative with respect to W5 times 1. And now we have known the derivative with respect to the output of the multiplication and with respect to the output of the sign. The task now is to figure out what is the derivative of the same output with respect to the inputs of the multiplication and with respect to the inputs of the sign. Again, using chain rule, we get the W3 adjoint multiplied by W1 and the W3 adjoint multiplied by W2. Here, the W2 and W1 are the partial derivatives of the multiplication. Also, the cosine is the partial derivative of the sine. And in this way, we obtain the derivative of the output with respect to the inputs. And the unique thing in this case is we obtain the derivative of the same output with respect to all the inputs, both inputs in this case, through one backpropagation. And that is why backpropagation is really the the ideal algorithm to use when you have many inputs, and which is the case for many machine learning applications. In machine learning applications, you really parameterize an unknown model with many different parameters, as we're going to see later on, and you perform an optimization to figure out what are the best parameters that leads to a best fit in some sense, in some statistical sense, with the observed data, right? And that gives you the best model to use. And no wonder backpropagation is kind of the bread and butter in machine learning these days.